I welcome you to this lecture of microscale transport process. What we have been discussing is the issue of dispersion in microscale chromatography. What we have discussed so far is how Taylor dispersion takes place when you introduce a slug at the inlet. Because of this parabolic velocity profile in a microchannel, that slug gets deformed, and then that leads to a different kind of mixing, which we refer this as dispersion. This is a different kind of mixing, and we try to at least put together the available theories that define the theories that define this sort of mixing. And then we said that this type of mixing can be a problem, or this type of mixing needs to be addressed in case of a chromatography type application in a microchannel. If I look at my PowerPoint slide here, what we see is that this we discussed in the last class, that solute transport in microscale chromatography. The objective of this is to identify components in gas or liquid mixture. This is happening because of accumulation of a component at the interface between two phases. Here by two phases, what we mean is one stationary phase, that is the adsorbent held next to the wall, and the other one is the gas phase, or the phase that is flowing, which is called a mobile phase. This accumulation is happening due to attractive intermolecular forces. A pulse of mixed solutes is injected into one end of a tube with inner wall coated with adsorbent. Now, solutes are adsorbed to different degrees and elute at different times. I try to explain to you this adsorption and desorption mechanism, and why a solute will be adsorbed, and then again it would be dissolved and it will elute at the outlet. And last point is the conventional chromatography utilizes packed bed. Microscale chromatography uses adsorbent coated inner walls of a channel, or a monolith coated with adsorbent. Basically, in a microchannel you probably cannot afford to have beads, which is commonly there in case of a macroscale chromatography. So, there would be some adjustment to it. Now, what we have done next is we mentioned that this technique may be compromised by dispersion. This technique may be compromised by dispersion. That means, the chromatography, when you run it, I mean at least this was showed in the last class, that when say you are introducing A, B, C, D, and they are eluting at different times. So, you get peaks of A, B, C, D at the outlet. Now, these peaks can get broadened because of this dispersion. And so, so to find exactly, if it would have been a sharp peak, you could have identified, okay, this is the peak. But if it gets broadened, there is always a possibility that some peaks get lost because of these dispersion. So, that's what probably the first point in the PowerPoint slide means. The technique may be compromised by dispersion. And then what we do here is we are trying to write down the governing equations. In the last class, we tried to put together the mass balance equation for the mobile phase. This is what we arrived at, right? This is the accumulation term. This is basically the radial diffusion, okay, and on top of that there was this axial diffusion, and this is the convective term as before. And we have discussed in the last class various boundary conditions. The initial condition is that you introduced a pulse at the inlet, and then when t greater than 0, you are assuming that at r equal to 0 symmetry exists, and at the wall and next to the adsorbent, not wall, at the interface between the mobile phase and the adsorbent, there exists this equilibrium, which is governed by this equation. You are assuming linearity here, and the continuity of flux. This is something which you assumed in this is something which we discussed in the last class. This is for the mobile phase, and for the stationary phase, what we have is that this is for the adsorbent, that means the stationary phase. So, that is why it was superscripted with a prime. So, concentration of that same species in the adsorbent phase, that this is the accumulation term and this is the radial diffusion, and I mentioned this in the last class that there will not be any convective term of course, and there could be some that axial diffusion is neglected, because you are assuming that the concentration gradient in the axial direction is not appreciable. So, here also you have a boundary initial and boundary condition. At t equal to 0, the entire adsorbent is untouched. So, C 1 prime is equal to 0, and at t greater than 0 at the wall, that means beyond the adsorbent. I am not talking about the, that means R is equal to capital R is the interface of gas and adsorbent, and R is equal to capital R plus delta, that means that gives the that is, we are talking about the wall beyond the adsorbent, and there isn't any diffusive flux there, that is the end of the story, because nothing can pass through. The tube is impermeable. So, this is d del C 1 prime del R equal to 0. So, this is something which you are working with. Delta is the thickness of adsorbent layer. So, these are primarily the governing equations and various boundary conditions that you can have. Now, what if I go back to the PowerPoint slide once again, I mentioned here that extended form of Taylor dispersion equation is used and 3 components of Ez term. What do we mean by this? What we mean by this is that you have what we write here is that C 1 bar. What was the original? I mean, this equation by now we have written it so many times. You should be able to write this. I mean, you don't have to refer any text. Okay, by rote you can just write this. So, this is the equation we had. All right, this is the equation we had earlier. This is the equation we had earlier. So, you have this is the equation, that same equation that we had earlier for Taylor dispersion. Now, what we are what is new here? What is different from the conventional Taylor dispersion is, first of all, we said that these Ez term we need to look into these Ez term once again, and also we need to look into this T 0. What is this T 0? Because this T 0 is something which is new to us. I mean, earlier we were working with T. Okay. So, the idea behind doing this exercise, I have already pointed out the governing equations. I have already pointed out that there are 2 governing equations, 2 mass balance equation, one for the solid phase and the other for the mobile phase, and there are boundary conditions or initial conditions that are in place. Now, you have to solve this equation, but your objective here is to I mean, at least the way the people have the researchers have thought about it is, what they have done, they have come up with this solution. They are saying that okay, this is the solution we have, okay, and let us now talk about the Ez and T 0 such that this becomes the solution of those 2 governing equations. Okay. So, that is what the researchers have already obtained. What the difference here is, what was the Ez term for say Taylor dispersion? You must be remembering V naught R naught whole square divided by 48 d. That was just a single term, small term. Here this Ez would be comprising of 3 different sum of 3 terms, because it is complicated and you are working with a different, more complicated equations than Taylor dispersion. So, this Ez has to be then that is absorbed in the Ez. So, what researchers have done is they have not touched this form, this functional form. They said that okay, let it be, because this functional form allows me to compare how things are, because this functional form was in place for just say diffusion of a small spot of dye in an infinite medium. So, let us continue with this functional form and write a compact expression for Ez. This okay. So, and see how this Ez is changing, because we started with D when we talked about the diffusion of a small spot of tracer in an infinite medium. There what we have done is we started with this expression, but there we had, instead of Ez we had D, that is diffusion coefficient. which is something we know, which is available, a bulk property. Okay. Then we said, okay, if we go to Taylor dispersion, we continue with the same form, but instead of d we have something called a dispersion coefficient Ez, and we said the expression for Ez you already know, V naught R naught square by 48 d, I mean that we have already looked into. Now, what researchers are saying is that we continue with the same compact functional form. However, we work with we work out how this Ez would be affected because of these complications. Okay, so that's a idea here. So what they have done is they have written Ez as sum of 3 terms, and those 3 terms are d into 1 plus k prime plus R naught square V naught square by 48 d into 1 plus 6 k prime plus 11 k prime square divided by 1 plus k prime plus delta square V naught square divided by 3 d prime into k prime divided by 1 plus k prime. Okay, now what is k prime here? First of all, the k prime here is equal to h delta divided by r 0. Okay, and T naught is equal to L divided by V 0 into 1 plus k prime. Okay, what do we have here? What we have here is, first of all, you got to understand that there, you got to appreciate that this equation system is pretty complex. Okay, you have already noticed this while when we try to at least identify the steps by which this Taylor dispersion has been the equation for Taylor dispersion has been arrived at. So this here you are working with the 2 different governing equations clubbed or put together. So this equation system is pretty complex. So one of the assumption here while arriving at this expression for Ez is that the adsorbed layer is thin. The adsorbed layer is thin. That means the delta is small compared to R 0. That is what it means. Now, this is one of the assumption you have. Okay, and this C1 bar is, of course, what is C1 bar? C1 bar is the concentration which is averaged over the entire cross section. I hope this you should keep in mind well, that 1 is species 1, the subscript 1 C1 bar, that 1 talks about species 1. If you have 1, 2, 3, 4, then you will have C2, C3, C4. Okay, and this bar represents the concentration which is averaged over the entire cross section. That means that you have a micro channel and at the outlet you have a detector, and the detector will detect the average concentration for the entire cross section, because detector will not detect individual layers. Though you have a parabolic velocity profile and one layer is moving at a higher velocity, but detector will detect over the entire cross section. Detector cannot detect that level, as such the dimension of the microchannel is small. So you so this C1 bar is the concentration which is averaged over the entire cross section. So this is the expression that you have here, this is the expression that you have here, and this is the expression for Ez. Now, as I said at the very outset, this Ez is comprising of 3 different terms. Okay, and these here we have made use of these, and the T naught is used here. Here we have used this T naught instead of T, and this T naught is given by this quantity. T naught is equal to L divided by V 0 into 1 plus k prime. Okay. Can you tell me what would be this L divided by V 0? I think this itself represents time. Only thing is, on top of that you have another factor added, which is 1 plus k prime. Okay. Now, what is k prime? K prime is equal to h delta by r 0. So, what is h delta by r 0? H delta by r 0, if I look at it here clearly, k prime is equal to h delta by r 0. So, this is basically equilibrium ratio of solute held in the adsorbent layer, held in the adsorbent to that inside the tube itself. Okay, that is what is K prime, equilibrium ratio of solute held in the adsorbent to that inside the tube itself. Okay, now this is K prime, and so what you are doing is, when you are writing this T 0 as L divided by V 0 into 1 plus K prime. If I write this once again, T 0 is equal to L by V 0 into 1 plus K prime. So, what this gives is this gives you the average residence time of solute. Okay. Now, if I try to, with this understanding, now if I try to identify what are these various terms in Ez, I said that there are 3 terms, that is, they are clubbed into 3 components. Ez has been clubbed into 3 components. So, where are they arising from? This first component d into 1 plus K prime, this is arising from axial diffusion. Okay. And here you have another term, this is arising from, I mean this must be obvious to you, we have at the as prefix R naught square V naught square by 48 d. So, this term is basically arising from Taylor dispersion. All right, and this term, this is arising from retardation in the adsorbent layer. Why there is retardation? Retardation in the adsorbent layer. Why there is retardation? Because you have this chromatographic effect present. So, this solute is getting adsorbed. So, this Ez is comprising of 3 different components. First component is arising from axial diffusion, the second component is arising from Taylor dispersion, and the third component is retardation in the adsorbent layer. And all these 3 components, they are contributing to the spreading of the spreading of that peak, and what you want to do is you want to minimize this spreading. All right. So, now if I go back to the PowerPoint slide, what we have here is we said that the technique may be compromised by dispersion, extended form of Taylor dispersion equation, that is what we have already written here, and it has 3 components of Ez term. Okay. The second term arising from Taylor dispersion, what that means is that making tube 10 times smaller can reduce this component of dispersion 100 times, because you have a R naught square type dependence. So, small channels are ideal for chromatography. So, smaller the channel, the better. Of course, you cannot endlessly, you cannot make this small endlessly, because you will encounter a very high pressure drop in that case. I mean, as you make it smaller, but at least from the dispersion point of view, that this is the smaller is the better. The third term arising from retardation in the adsorbent layer. Third term is arising from retardation in the adsorbent layer, that you have already pointed out. These, if diffusion in the adsorbent is very fast or delta by R 0 is much less than 1, no effect of third term. On the other hand, the separation due to adsorption becomes dominant when K prime is much greater than 1. What do we mean here? Let us focus on what I have written here. On the third term, we have this diffusion in the adsorbent. When the diffusion in the adsorbent is very fast, diffusion in the adsorbent is very fast means this d prime is very high. When the d prime is very high, automatically the value of this component would be low, okay? Or delta by R 0 is much less than 1. Delta by R 0 much less than 1, that means delta square would be very small. So, either d prime is much higher or delta is much small, both have the same effect, that will make this term insignificant. Okay. On the other hand, if k prime is much greater than 1, if k prime is much greater than 1, then the separation due to adsorption becomes dominant. So, this term becomes dominant if k prime is much greater than 1. If k prime is much greater than 1, then this will cancel out and this remains there. Okay. But if k prime is much smaller than 1, then this term would be much smaller. So, this is the idea here, that because your objective here is to reduce this Ez as much as possible, then only you can have this in the C1 bar, you can have least amount of spreading, the concentration profile. I mean, you have put a peak here, you put a peak here, this is the peak you have given, and what you get at the outlet of the tube is something like this, and you want to minimize this. Ideally, you want this peak to be, this also should come out as a peak. So, how you can reduce this broadening is you can reduce this Ez term, and for reduction of Ez term, of course, one thing is you can reduce this R 0 to the extent possible. I mean, without hurting, I mean, because there will be huge amount of pressure drop, and pressure drop means that even if you keep the outlet at atmospheric pressure, the inlet of the channel will have very high pressure, and it will the first place it will start leaking is through the port through which you are injecting. So, this is the problem there, or otherwise you can play with the third term and you try to reduce this. I mean, or I mean, in case the d prime is big, d prime is high, then denominator is high means this quantity will become smaller, or if delta is low, that means delta by R 0 is low, then also this will become smaller. So, that also can help you in reducing the broadening. So, this equation sort of this expression for, so we do not care about this expression, this equation anymore, because this is the same equation that we have been talking about, but we focus on this Ez and we see how much would be the spreading, or if we have two different systems, how much spreading will take place for each case, which one will have broader peak and which one will have sharper peak. So, that can be worked out through this equation system, through this functional form. Now, if what you need to look at in this PowerPoint slide is that different solutes will have different retention time T 0 depending on the k prime of corresponding solute. What is T 0 here? If I look at these what we have written here or here, T 0 is equal to L by V 0 into 1 plus k prime, and k prime would be different for different solutes. We have 1, 2, 3, 4. For 1 you have some k prime, for 2 you have another k prime. So, you have depending on the value of the k prime, it would be different solutes will have different retention time. Objective here is to make Ez tending to 0. Ideally, Ez should be that spreading should be made close to 0. So, that each solute elutes as sharp pulse. However, for broadened peak, the pulses overlap and identification is compromised. This you have appreciated. R naught and V naught should be decreased to achieve Ez tending to 0. R naught, because R naught, V naught, they are appearing in the Taylor dispersion term in the second term. So, R naught should be small, V naught should be small. Okay, R naught and V naught should be decreased to achieve Ez tending to 0 as long as pressure drop is not excessive. Now, if V naught is reduced, the pressure drop would be less, but if R naught is also reduced, then that will have an adverse effect on the pressure drop. So, you are that the system has to be designed appropriately, but these are the, at least from the dispersion's point of view, these are the terms, and this is the type of dependence you have as far as the broadening of the peak is concerned. Okay. So, this is this is I think all I have as far as the dispersion is concerned. we have talked about first of all the difference between a diffusion and a dispersion, and we have come up with a functional form just for diffusion, and we retained that same functional form C 1 bar. We retained that same functional form, and then we continued defining what is Taylor dispersion, and we showed that in case of a chromatography in a microchannel, what all terms would be playing, but retaining the same functional form, how the individual terms would be affected because of various contributions from various parameters. So, with that practically I would be closing this discussion on dispersion. The next topic that I pick up here is on electro kinetics. Okay. So, this is a new topic. So, we are moving away from mixing. So, we started with first we discussed about the fabrication of various devices, then next we worked on passive mixing, and we tried to show that remaining within the framework of that same mass balance equation over a differential element, and then taking the solution, how we can mix and match, how we can have elongational deformation or linear stretching, and we are basically in between somewhere, but the two extremes we discussed, and various how we can treat this mixing, how we can derive, how we can obtain a functional form for mixing, and what are the various passive mixers that are available, various mixing schemes that are available. And then next we said that there is a problem in hand here, which is called dispersion, which can have adverse effect in this dispersion is also another form of mixing. However, this mixing is unwanted. The passive mixing that we have discussed was the desired mixing, but here it is not desired. However, you cannot avoid it because it is defined by the fluid mechanics itself. So, next topic that we pick up is something called electrokinetics. Okay. Electrokinetics basically it concerns interaction between solid surfaces, ionic solutions, and macroscopic electric field. Okay. Interaction between solid surfaces, ionic solutions, and macroscopic electric field. So, all these three aspects are involved here. We are mostly focusing on electrophoresis and electro osmosis here in this lecture, though there are other forms of electrokinetics, there are other forms also present. Here we are not talking about electroweighting. I think that would be taken up separately. I mean, it will not be taken up by me. This electroweighting is another very important topic, where basically the contact angle gets changed, but that is not we are taking up here. We are mostly focusing on electrophoresis and electro osmosis. Now, these both are manifestations of electrostatic component of the Lorentz force on ions and surface charges and Newton's second law of motion. So, here you are talking about electrostatic component of Lorentz force on ions and surface charges. So, you are looking at first of all the electrostatics, okay, the electrostatic forces, and also you are looking at the Newton's second law. So, it is a mixture of both. Basically, what we will write is we will write down the our governing equation here in these scheme of things would be Navier-Stokes equation. However, we have additional body force term arising from these interactions, these electrostatic components, etc. So, basically we are working with the framework of Navier-Stokes equation only with an additional body force term. So, that is basically this what we would be working on, and this so now we define quickly what is electrophoresis and what is electro osmosis. Electrophoresis is induced drift motion of colloidal particles or molecules suspended in liquids due to an electric field. Okay. And electroosmosis is motion of electrolyte liquid with respect to fixed wall due to electric field applied parallel to the surface. What are these now? Electroosmosis, motion, what is the last point? Motion of electrolyte liquid with respect to a fixed wall due to electric field applied parallel to the surface. What that means is, suppose you have a surface here, okay, and you have an electrolyte present on the surface. What is an electrolyte? I mean, how would you define that? For example, say NaCl breaking down into Na plus and Cl minus, something like that, which is giving you ions, okay, there, okay, and you have a surface here. Now, you can say that, okay, first let me tell you what will happen here. For some reason, this surface will acquire some charge, maybe positive or negative. What could be the reason of this charge developing on this surface? There are various reasons possible. In fact, if we look at this PowerPoint slide, solid surface acquires surface charge when brought into contact with an electrolyte liquid due to, there are 3 points given here: differential adsorption of ions from electrolyte onto solid surface, differential adsorption of ions from electrolyte onto solid surface. So, this solid surface is these ions that are present here, ions are present plus and minus, these ions are roaming around everywhere on top of the surface. There is differential adsorption, that means some particular ions are adsorbed more by the surface than other, and thereby you are developing some extra charge. The second point is differential solution of ions from the surface to the electrolyte. So, from the surface something is going back to the solution, from the surface something is going to the solution, some differential solution of ions. Differential solution, that means differential means plus is more than the minus, okay. That is what I mean by differential. So, differential solution of ions from the surface to the electrolyte. Or the third point here is deprotonation or ionization of surface groups, such as surface silanol group of glass or silica. Since we have been extensively talking about glass and silica, we have been talking about this glass as a microchannel device, as a material for microchannel device. So, that will have silanol group SiOH, which breaks down into SiO minus and H plus. Okay. So, this H plus is available and this H plus goes away. So, these gives, so you have deprotonation of the surface group. So, if H plus goes away, so automatically the minus charges, they are left there, and these minus charges will be sitting there. So, the surface will be having all minus charges. All right. So, for various reasons there could be some charges may develop on the surface. Deprotonation is most common. What we have here, deprotonation is most common, and net surface charge density at the liquid solid interface is a function of local pH. Full deprotonation at pH greater than 9. Net surface charge density at the liquid solid interface is a function of local pH. I mean, this you must appreciate, because pH is what? It gives you some what is the hydrogen ion concentration, right. So, what pH you are holding the surface at, that has a tremendous effect on how much H plus is going from the surface to the electrolyte. So, the local pH is functional to local pH. Net surface charge density at the liquid solid interface is a function of local pH, and full deprotonation at pH greater than 9. So, this is a fact which is there. I mean, if you have a surface, you will develop some charge there, and because of this charge developing, the opposite charge from the electrolyte would be attracted to the wall. So, if you have all plus here, you will have all minus sitting here like this. Now, this is happening with any wall material. So, if you have a pipe on the wall, this is happening, but for a macro scale you probably do not care much about it, because this is insignificant. But in a micro scale, when it comes to a micro channel, these particular phenomena can be important. I mean, because of the scale of the problem, these particular phenomena needs to be studied. Okay. So, what we have is ions of opposite charge in the electrolyte are attracted and the like charges are repelled. So, opposite charges are coming to the wall and the like charges, that means the plus, that will be repelled from the surface. That is the idea, that is how it happens everywhere. Net excess of mobile ions net excess of mobile ions near the interface with charge opposite to that of the wall is referred as EDL. Electric, the full form is electric double layer. Okay. These excess charges can be used to impart a force on the bulk fluid through ion drag. These excess charges can be used to impart a force on bulk fluid through ion drag. What is meant here, or what this statement means here, is that if you have a channel, then you will have, similarly the upper part of the wall also will have, these positive. See, you have a flow between two parallel, or you have two parallel plates. We have not talked about flow. We have say we have two parallel plates. So, the upper plate also will have the same thing, and then you will have opposite charges attracted to it, all right, and then these other charges are floating around here and there, right. So, what this is saying is that you will have the concentration of some opposite charges next to the wall. Okay. Of course, there would be one layer which is immediately adjacent to the wall, which would be so called a static layer, okay, which is static, but there would be a diffused layer. I mean, it would be up to some distance away, there would be a concentration of negative ions. I mean, there would be some positive charges, but the negative ions, the concentration would be more, and that is a diffused charge, which is a mobile charge, which is mobile. Okay. So, maybe immediately next to the wall there would be a compact layer, but little bit away from there is a concentration of opposite ion which is mobile. Okay. So, that is very much present around. And of course, the positive, because positive and negative, they have to be equal, should be in equal numbers. So, then there are positives everywhere. Okay. So, this is next to the wall, and this is probably the away from the wall, which is probably you would say the bulk. Okay. Now, if you put the electrodes, here, suppose you put an electrode here, this is an electrode here and this is another electrode here, okay, and then you put this electrode here and you put, so this is acting as an anode and this is acting as a cathode. So, what will happen is these negative charges, they would be pulled towards this direction, these negative charges would be pulled towards this direction, negative charges from the diffuse layer, the negative charges which are mobile, which are free to move, which is not sitting next to the wall held permanently, but which is free to move. So, that would be moving, and that while these ions are moving from one direction to the other, this is generating a drag force. This is generating. So, if I look at the PowerPoint slide, what we see here is that ions of opposite charge, if we look at the PowerPoint slide here, the ions of opposite charge in the electrolyte are attracted and the like charges are repelled. The net excess of mobile ions near the interface with charge opposite to that of the wall is referred as electric double layer. These excess charges can be used to impart a force on bulk fluid through ion drag. So, now if I look at what I have drawn here on this page, what we are saying is that these negative charges will be pulled to one electrode, okay, and the positive charges, I mean negative charges will be pulled towards one electrode, okay, and this while this pulling, it would be pulling there would be a bulk, there will be a force on the bulk fluid through ion drag. So what in fact we can show that from Navier-Stokes equation we said there would be a body force term, right, an additional body force term coming in here. So what we will be doing here is from the Navier-Stokes equation we can show that okay, there would be viscosity, there would be everything, but because of that body force term, that extra body force term that we are talking about, because of that body force term there would be a net movement of the fluid from one direction to the other, and that is arising because of this body force term, as I said. So you can call this that these excess charges can be used to impart a force on bulk fluid through ion drag. That is what you can say here. All right. So this we will get into the theories of it, how we can really have. In fact, what we will do is I will give you the velocity gradient, I mean what is delta v, and I will ask you to find out what would be the velocity. Okay. So you will be having those theories in hand, how we can find out the velocity here. In fact, this is one pumping mechanism people have researchers have proposed, electro-osmotic pumping. I mean you might have heard of this term. So this is based on this principle. So I mean why I have gone so far here is, if we now look at what we have said so far, I repeat once again what we have what we studied before here, what we learned here is that interaction between solid surfaces, ionic solutions and macroscopic electric field, that is what we are talking about here. We will be discussing about electrophoresis and electro osmosis here. Both are manifestation of electrostatic component of the Lorentz force on ions and surface charges, and Newton's second law of motion. Now if I look at the electro osmosis, the second the last component, electro osmosis is motion of electrolyte liquid with respect to a fixed wall due to electric field applied parallel to the surface. Do you agree to this, what we have discussed here? Here on this paper, what we have discussed is basically the motion of electrolyte liquid with respect to a fixed wall. The wall was fixed, electrolyte liquid is moving due to electric field applied parallel to the surface. All right, field is applied parallel to the surface, field is in this direction. So field is applied parallel to the surface. Okay. So that is what is referred as electro osmosis. Now if we look at what is electrophoresis in the PowerPoint slide, induced drift motion of colloidal particles or molecules suspended in liquids due to an electric field. What that means is that you have similarly a positive and a negative electrode, and you have a colloidal particle, or think of a particle altogether. You have a particle. Okay. You have a particle. If the particle is big, one can show that you have an electric double layer developing around the particle, and this particle as a whole will be pulled to one electrode. On the other hand, there would be drag force acting on the particle, because moving a particle to one electrode, it has to overcome the drag force. So there would be an interplay between the drag force on the particle and the electric double layer that is developed around the particle, which would be pulled by the electrode. So this would be another game where these concepts of electric double layer will be important, but in a different way. So this sort of scheme is referred as electrophoresis. So depending on what is the size of the particle, etc., that will be, or how much of charge it has on the particle, it will be pulled by different velocities. Okay, and velocity, by that I mean the terminal velocity. So that means if you take this system, apply the voltage, run it for some time and then freeze it, then you will see that over that delta t time, each particle is moved by some distance depending on the size of the particle and depending on the charge that it has. So you will find that the particles of same size or particles of same charge, they will be forming band. Okay, and by identifying these bands, you can, or probably from pre-calibration and then running the sample, then you can identify, okay, the particle is having these properties, or the sample that you have, it contains A, B, C, D, and A is of this size and this charge, B is of this size, this charge. So, this kind of analysis you can do. So, these are essentially. So, what I want to mention here is we understand the interaction between solid surfaces, ionic solutions, and macroscopic electric field. We understood what is at least that interplay of electrostatic component of the electrostatic components and these Newton's second law of motion, and I mean we have some idea of what is it. So, electrophoresis is induced drift motion of colloidal particles or molecules suspended in liquids due to an electric field, and electro osmosis is motion of electrolyte liquid as a whole. Okay, this we already discussed. So, this is what we had. Now, this electric double layer, once again the solid surface, why solid surface will acquire a surface charge, because when it comes into contact with an electrolyte liquid, there are so many things that can happen. 1, 2, 3, deprotonation is most common, and of course, the pH has a good effect on the. So, the net surface charge would be function of local pH. Then we said that these ions of opposite charge in the electrolyte are attracted and the like charges are repelled. The net excess of mobile ions near the interface with charge opposite to that of the wall is referred as electric double layer. These excess charges can be used to impart a force on bulk fluid through ion drag, and the counter ions reside in compact layer next to the wall, which is referred as the Stern layer, that is in adsorbed state, and counter ions also reside in more diffuse layer next to the wall, where the ions are free to move. Now one thing I would like you to appreciate here is that if I look at what we are writing here on this paper, we said that we have some charge. Okay, we have some charge here. So, these are all this is the wall, and we have positive charges here. This is, I mean, so then I mean even if this wall is a metal, still we can have this kind of charge. There would be a layer which is referred as Thomas Fermi layer. The thickness of this layer is maximum, it goes to 0.2 nanometer, even it is less than that. That is where these charges are predominant. Okay. Beyond this, I mean these when it comes to metals, I mean it has electrons, it has they have practically excess charges available. So, essentially what these researchers they have they found is that these charges are heavily screened in the sense that these charges will remain this way. I mean, it will not, you will not expect, even if this is a metal, that these charges will escape. Okay, so there is a screening involved. This screening, this is referred as the Thomas Fermi layer, within which there would be concentration of charges, but that does not, because as such there would be a lot of charges inside. I mean, there are a lot of I mean, I do not want to get into the distribution of atoms, etc., but there are available charges as such, which will ensure that these charges are screened next to the wall up to a distance which is less than 0.2 nanometer. That is what you have to keep in mind. Though, so even if you have a metal wall, still you can have this possible. Okay, it is not, it need not be, it has to be a colloid or something like that. So, this is what you have, one thing. Second thing is this existence of this opposite charge. So, this is the end of the wall. So, this bold line is the wall. So, these plus this is little bit inside the wall. Now, immediately outside the wall there would be opposite charge, we said, right. So, you will be having a very small distance, where these negative charges are held. One thing I want you to appreciate, I mean, this we are still working with the framework of whatever we studied in a macroscopic scale. So, there would be, say, adsorption of neutral atoms possible on the wall. So, it is not that it will be all arranged plus and minus. There could be a large large neutral entity sitting there, adsorbed on the surface. There could be so many other things happening, but as far as the charges are concerned, they are there. That is what, and since we are talking about electric double layer, so we are only focusing on charges. We are not talking about other entities, but there will be other entities also present. For example, a neutral molecule will be adsorbed on the surface, and which is very much possible. There will be adsorption, desorption, everything is going on. Plus, on top of it, there would be these array of charges present. Now, this layer, a very small, very thin layer, where the charges which are there inside this layer, these charges are held strongly. These charges are held adsorbed to the wall, and these charges are referred as this layer is referred as Stern layer, STERN, Stern layer. Now, this existence of this layer, I mean, it is very difficult to confirm. I mean, what exactly is happening? In fact, the researcher who was doing the pioneering work here is Helmholtz. Helmholtz is the person, but in fact this layer, in a lot of places you will find that initially it used to be referred as Helmholtz layer. Okay. Now, the problem was there is that this layer, what researchers have found is that there exists another layer which is probably much on a wider level, where you have predominantly minus charges and some plus charges as well, some plus charges as well, but predominantly minus charges. Okay, but some plus charges here and there. Okay, and these charges, they are mobile, they are not adsorbed by the wall, they are mobile, and these charges can be pulled by application of by putting an electrode. These charges can be pulled, and these charges can give body force to the Navier-Stokes equation and pull the rest of the liquid as a whole. Okay, so these charges is what matters. Okay, so then probably they differentiated into these Stern layer, which is next to the wall, and these diffused layer. It is this called Chapman layer. There are various scientists who have. So, initially it was some proposition, and then later on, initially there it was proposed from the free energy point of view, from thermodynamics point of view. Okay, and then they said, okay, there should be provision like this, and then people have showed, I mean, electroosmotic pump is in existence. People have showed movement of fluid by this method. So, then naturally there has to be a diffuse layer. So, then these things continue to develop. Okay, I have to wrap up this discussion here. What I will do in the next class is I will start solving. I mean, I will start writing the governing equation that defines what would be the concentration of plus ions, C plus as a function of Z, C minus as a function of Z. What is Z? Z is distance from the wall. Z is distance from the wall. So, how the plus concentration changes with Z, how minus concentration changes with Z, because this information is very important. Once we have that, then only we can write down the body force term in Navier-Stokes equation, and then because our final aim is to find out what would be the velocity. Okay, from Navier-Stokes equation, I do not apply any pressure drop. I do not apply any pressure. Delta P, I mean P inlet and P outlet, they are held at same pressure. P inlet and P outlet held at same pressure. I have applied just the voltage, and now I am seeing the bulk movement of the fluid. And what is the velocity? What is the average velocity by which the fluid is moving? That velocity I have to find out. So, I have to use Navier-Stokes equation only with the body force term would be arising from these ion drag. So, before we find out, it is very important that we find out how the concentration changes, plus ion concentration and minus ion concentration, because here you can see the minus ion concentration would be higher at z equals to 0 and then it goes down. Then if that is so, then the opposite ion concentration would be just the reverse. So, what would be the functional form? So, we will start from there. So, in the next class we will start from there. That is all I had for today's discussion.